very important data structure, right? Graph is a very important data structure because it allows us to go from one place to another place, has many applications. For example, routing problems, roads, highways, mapping problems, modeling, connectivity of electronic components. I mean, the graph can be connected virtually unlimited applications of the graph. And so we looked at how do you represent a graph? And we looked at the adjacency matrix, which is just a matrix, which is 0 or 1 if there's a connection. We also looked at adjacency list, which is a vector of all the vertices, which has a linked list to only its immediate neighbors. That's another one. Sometimes we have unweighted graphs, and sometimes we have weights, graphs that have weights, so sometimes links have weights. If we do a matrix, we could have, for example, 0 if there's no connection, 5 if there's a weight of 5, 1 if there's a weight of 1. So that could be any non-zero value could be weighted, and of course we can put the weights also into an adjacency list. So now, because graphs can be directed or undirected, starting at one vertex gives you access to lots of other vertices, but maybe not necessarily all the vertices. Okay, so for example, if you start at vertex A, you could go to B, B might take you to C, but then it can't take you to D, but maybe it can take you to F, and maybe F goes to D, so somehow you can end up at D. But there are some vertices you can't reach from a starting vertex. So that's why we have the traversals. And traversals gives us a set of vertices that are reachable from any given starting vertex. So given that we do a starting vertex, let's say at A, we may be able to visit these vertices. But if we start at C, we might be able to only visit 2 vertices. But if you start at F, you can get all of them, for example. So it changes. So the way we traverse, the traversals that she introduced, I think, are called breadth-first search and depth-first search. Depth-first basically means that you are a vertex, you're starting here, and you say, okay, I have 3 neighbors. So you basically say, okay, I'm going to go to my first neighbor. And then from here, I'm going to behave like I did before. I'm going to look at my neighbors, and I'm going to go to my first neighbor. So I'm going to ignore these 2 neighbors, and I'm going to ignore the other neighbors. I'm just going to go as deep as I can, depth first. And from here, I can go to 2 different places. I can go here, or I can go here. This is my next neighbor, but I've already been there. It's visited. So I'm not going to go there because I marked it off. Never go there again. So I'm going to go here. Then from here, I can't go anywhere. All right, so that means I visited here, 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 and here. Can't go anywhere, so I recurse back. Last time I was here, I went here, and I couldn't go here, so I'm going to recurse back. Last time I was here, I had 3 choices. I went here, so now I'm going to try to go there, and then I'm going to go deep as I can. So you choose one of your neighbors, and then you recursively go as deep as you can from those neighbors, and you keep doing that until you visit all the nodes you can, and until all the nodes have been visited. Why do we have to mark the unvisited nodes? What if we didn't do that?
The path that you have already been visiting.
Yeah, and what would that, so would we ever finish our job? We would never finish our job if there was a what in the graph? Cycle. So if you had A goes to B, goes to C, goes to A, and you never kept track of it, then basically when you went to A, you would go to B, from B you would go to C, from C you would go to A, from A, then that's a problem. So once you go to A, you mark A. You go to B, you mark B. You go to C, you mark C. C, the only neighbor is A. Well, I can't go there. I've already been there before. I have no other neighbors. Then go back to B. Last time I went to B, I went to C. Do you have any neighbors? Yeah, I have F. Go to F. Where else can you go from F? I can go back to A. Nope, been there before. I can go to B. Nope, been there before. Then go back. Last time I was here, I went here and here. I have no other place to go. Then go back. So eventually you're going to recursively come back, and you're going to visit all the possible vertices. So that's depth first. Then we had another one called breadth first. So breadth first basically means that if you start at a vertex and you have 3 neighbors, you're going to visit the first neighbor, the second neighbor, and the third neighbor, and you're going to put them all into a queue. So then after you visit the first 3 neighbors, the first of the visits is going to be in the queue. You're going to remove it. And then you're going to visit all its neighbors. And you're going to put them in the queue. So what the queue is going to contain initially the first vertex, which is distance 0 from itself, then all its neighbors, which are distance 1 from itself. Then you're going to get all the neighbors of the first one away from the from the starting vertex, boom, 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 distance of 2. Then you're going to get all the other ones from a distance of 1, boom, 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 2. And this one may be another one of 2. So when you finish all the 2's, all these are going to be 3's, and you're going to go to their neighbors. So you're going to visit each of the vertices as early as possible in terms of the number of edges that you'll cross. Okay? So for the depth first, the algorithm required recursion. But for the breadth first, we required what data structure? We required a queue. So you put things into the queue. All right. So now we're going. So now we're going to talk about 2 algorithms today. One is going to be, if we have time, I think we have time. So the first one is going to be the shortest path. So there are going to be 2 algorithms that I'm interested in today, and one is the shortest path, which means the fewest edges to go from start to finish. Fewest edges. So for example, if I want to go from A to B, and I can go from A to B in one edge, done. Okay, that's all I'm going to do. Notice that I can go from A to B to D, or I can just go A to D. So if I want the shortest path, it probably makes more sense to go here. Okay, so shortest paths will be the fewest edges. So how am I going to do that? I'm going to utilize one of my traversals to do that. The best traversal to utilize is I want to keep track of how I can get the soonest, fewest edges to the destination from the start. Which of the 2 traversals do you think I can modify? Breadth first. Because we don't want to go too far. We want to go like this. As broadly as possible. We want to go deep, because then basically I might go doop, 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 get someplace here. Okay, so I'm going to use breadth first search. And you're going to see how, so remember how breadth first search works, right? So we're going to modify it. So let's take a look at it. So basically, let me explain to you this technique. So the first thing is, we're going to go from a starting vertex. So let's say I want to start at vertex D. Okay? I don't know why. It's not because my name starts with a letter D, but so I want to go to D. Start with D, and I want to end up, let's say, at J. Yeah, for some unknown reason. So if I start from D, then basically what it is that I'm going to have some starting vertex. So start is going to be my starting vertex, in this case D, and maybe my ending vertex is going to be J, and destination will be J. So that's, and I can change those anytime. So the first thing I'm going to do is I will explain to you some of the notation here. So dist is a vector. So basically for every vertex in my graph, I'm going to put a -1 under that vector. And that means it has not been visited. Okay? -1. -1 means unvisited. Now, the next thing I'm going to do is I'm going to visit the starting vertex. So in this case, D. And I'm going to set distance, dist, which is a vector of the start, to 0. And so let me explain to you what dist is. It's a vector of distances from the beginning. Since I am at the beginning, the distance from the beginning to the beginning is 0. That makes sense, right? Okay. Now, this is not a vector. Distance is a scalar, just a number. So distance basically will be a number. How many steps are you from the beginning of the graph? Well, since I am right now just visiting start, my distance is 0. Now, what I'm going to do is I'm going to initialize my queue to contain the starting vertex. So the starting vertex is D. Okay? Now, while the destination J has not been visited, has not, and the queue is not empty, it's not, because D is in it. Remove D into V. So V is going to be the current vertex from which I am going to be looking at neighbors. So V is going to take on the value, what I just removed from the queue. V is going to take the value of D. And then if the distance of V, what's that? 0, is greater than distance, so that's false, so we don't do this. And you'll see why in a minute. We will do it later. Now, so what I'm going to do is I'm going to loop. And so this loop basically will be an iteration over the neighbors of V. Remember, V is representing D. So For each neighbor W from V, if you haven't visited that neighbor, then go to the predecessor vector of that neighbor and set it to V. Remember, I'm going from V to neighbor W, from V to neighbor W, another W, and another neighbor. And all those neighbors, I came from V. So therefore, the predecessor of W is V. So for example, if V, which is D, representing D, vertex V, has a neighbor EFG, then the predecessor of E is D. The predecessor of F is D. The predecessor of G is D. So predecessor tells you where you came from to get here. And notice that I've come to EFG as fast as possible, because basically I went there from the start immediately to those places. Right? So for every neighbor from my vertex V that I remove from the queue, visit all its neighbors as W, and set the predecessors of those neighbors to V, and visit that node, set the distance of that one to distance plus 1. Remember, distance is how far am I right now from the beginning. Well, right now I'm still, V is still D, so my distance is still 0. So therefore, distance plus 1, that means the distance of my EFG neighbors is going to be 1 more than I currently am, because I'm looking at neighbors and I'm at 0, so they must be at 0 plus 1. So all these distances get a value of 1, 1, 1 for all the neighbors. And for each of them in turn, E, F, G, I add them into the queue. Notice the queue right now, after I got into the loop, is empty, but now it's been reloaded with E, F, and G, which are 1, 1, 1 step away from D, which has been already processed. Okay, so now, what's at the front of the queue? D. E, F, G. E, F, G, so D is already out, so E, F, G is in the queue. Now, has the destination been visited? No, because J has not been visited. And the queue is not empty? No, it's not. So, remove vertex V from the queue, and that time it's going to be E. So now E is the new V. Vertex V is now representing the vertex E. Now, is the distance of V more than distance? Well, dist of V, which is E, is 1, and distance is 0, therefore it's true. So what happens is distance moves to 1. What does it mean? That means the current vertex right now is 1 step away from the start. Therefore, all my neighbors at this point that have not been visited, when I go to them, I'm going to mark their dist as plus 1, which is going to make them 2. Make sense? Okay, and it will continue this way. So this is the way it's going to look. So now let's take a look. So now I'm going to go through, there's an algorithm defining the path, but I'll just show you. So we were going to use this particular graph. So trying to go from A to E. From A to E. Notice that there's a lot of ways to get to A to E. There's this way. There's this way. No, that's not a way. There's this way. Okay, bunch of different ways, right? Okay, so notice let's remember this. So A is my starting vertex. Who are the immediate neighbors of A? B, C, and D. Okay, now when I do this algorithm, I would prefer if I'm going to visit my neighbors alphabetically. So therefore, if A has neighbors B, C, D, I'm going to go to B first, then C, then D, and that makes everybody's answers standardized and probably a good idea. Okay, so we're going to go from A to E. So notice that my distance vector basically says how far are you from the start? Well, the start is A, so A is 0. But these guys, -1 means, I don't know. That means we don't have a registered yet. Predecessor, we haven't registered yet. So who is your predecessor? We don't have that yet. And visited, basically, we can put a mark of 1 if we've been there before. So initially when we visit A, we're going to mark 1 as visited. The distance from A to A is 0, and the queue contains A. And now it's time for us to remove from the queue into the loop. And so what's going to happen is V removes A, and the queue becomes empty. And now we're going to iterate over A's neighbors, B, C, D. Okay, so W is going to become B first, then C, then D. B is not visited, so set the predecessor of B to the A. Visit B, The distance of B is 1. Why 1? Because distance is 0. 0 plus 1, you're 1 away from the vertex V, which is A. So the Q contains B. Now go to the next neighbor of A. That's C. Not visited. Okay, so set the predecessor to A also. Okay, and visit it. Mark the distance vector of C to 1 also. And the Q contains B and C. And now go to the last neighbor, which is D. D has also not been visited. Predecessor goes to A. Visit it. Set the dist of that vector to 1. The Q now contains B, C, D. So now we're finished with the inner loop. We're going to go to the outer loop. We're going to find out if we have visited our destination. The answer is no, because the destination is E. So therefore, what are we going to do? So let's see what's going to happen here. So the dist here is 0 from A, 1, 1, 1 from the neighbors, and these guys are untried. Predecessors, B, C, and D are all A. And visited vector contains A, B, C, D, but not E, F, and G. So now we're going to remove from the Q B, that leaves in the Q C, D. And the distance increases to 1. And so now we're going to look only at the neighbors of B, which are going to be C, D, and G. C was already visited, so the loop quickly shortcuts, and there's nothing to do. Now W takes on the value of D. D was already visited, so we're done. And now we go to W, takes the value of G. G has not been visited. So the predecessor of G gets the current V, which is B. We visit G and set the distance of it 1 more unit than how far B is from A. And the Q contains now C, D, and G, because B has been removed, right? So which one is next coming out of the Q? Is going to be C. Notice when C comes out, it's not going to increase distance variable, because its distance from A is still the same. So therefore, it's not going to increase it. So when C comes out, it's still going to be 1. When D comes out, it's still going to be 1. When G comes out, if it ever comes out, it's going to go to 2. I don't think it's going to come out. Okay, so C is going to be, so this is our state right now. So our distances are here. Notice that G has a value of 2. The predecessor of G is B, and visited adds G. So now our Q, we're going to remove C from the Q. So C comes out of the Q, leaving D and G. Distance is equal to 1, it stays put. The neighbors of C are E and G. We mark the predecessor, we visit E. We mark the distance at 2. And the Q includes D, G, and the new E. When W goes to G, G was already visited. So algorithm terminates now because E was visited. And that was our destination. So algorithm terminates. So the final state of the tables look like this. So we have this set here. Basically, we never got to F, but we don't care about that. And we have our predecessor vector. Notice that our target was what? E. And our visited, again, we never got to F. That's marked here. Now, I want to find out what's the path. So first of all, I terminated because I got to my destination. So what's my path? Well, my path, I go to E, and it says the predecessor is C. So I push C on the stack. And I go to C. And I say the predecessor is A. So I push A on the stack. But A is the start. So that means to get to destination, I'm going to pop, and I'm going to get A.
C.
Then I'm going to get C, and I'm going to get E. Okay, and the algorithm to do that, basically, finding the path looks like this. So basically, you quit the algorithm when you can reach from a particular V value, the destination W value. So that means the distance has the value of the V. But the target is really 1 unit away more, and that's why we always increase the distance by 1 after you quit the loop. If the destination has not been visited, but you quit the loop, then you can report the destination is not reachable from the start, and that's the same thing as breadth first. This is really breadth first search, guys, right? Same Q, except that we're keeping these vectors to keep track of where we are. Else, we're going to say the path vector, path 0 is start. So we're going to say A is the value of path 0. then path distance equals destination. Destination is E. So path sub distance, path sub 2, is going to get the value of E. And now we're going to loop. For I equals distance minus 1 down to 1, the path sub I is the predecessor of path of I plus 1. And it's going to fill in the path going backward. So once you do that, then you can, instead of pushing and popping on the stack, what you can do is you can just iterate from path 0, 1, 2, 3 up to the destination. Or up to the distance, I'd say distance minus 1, because 0 is the first one. Okay, makes sense? And I was going to do one more algorithm, but I think I'm out of time. I do have another important class to teach. The students would be so disappointed if I didn't show up. All right, so I'll make a couple of corrections on that. I'll double check that work. I think that is an error. So, soon we'll have another homework assignment.